First, thanks for the introduction, and thanks for the organizer for inviting me here. So today I will talk about probabilities of causation. So probability causation are a family of probabilities quantifying whether one event is the cause of another. So they are valuable concepts in AI applications for decision making, for causal explanation, for assigning responsibilities, assigning blames, and so on. So the original definition of POC are limited to binary variables. So in this talk, we aim to extend this concept to continuous variables, since in many applications, people are often interested in continuous variables. And also, we will provide causal mediation analysis for POC. So causal mediation analysis are concerned about analyzing causal effects through different pathways, like direct effects or indirect effects. So I will aim to provide new variants of POC. We talk about, say, direct POC, indirect POC, and so on. So that's what this talk about. So first, some background. Initially, POC are defined for binary variables. Like assume we have a binary treatment variable x, say taking two values, x0, x1. Let's say x0 is false, x1 is true. So whether this event is present or not present. So y is the, say, binary outcome variable. So Pearl defined three kinds of probabilities of causation. So there is this, is there laser pointer? No. So there's this probability of necessity and sufficiency. So probability of necessity, for example, the probability of necessity assumes that if you are given the presence of x and y, they both occurred. You ask, had x not occur, would y not occur? What's this probability? So intuitively, this quantifies the necessity of the presence of x to cause y. So similarly, there is this probability of sufficiency, which says currently x and y does not occur. You ask, had x occurred, would that cause y to occur? So that quantifies the probability of the sufficiency of x. And then we have this probability of both necessary and sufficiency. So this kind of three quantities define some kind of the intuition about the necessity or the sufficiency of the one event of x causing the event of y to occur. So that's the original definition. And we also notice that all these definitions, they are some kind of counterfactual quantities. So you cannot directly observe them. So they are very useful concept in practice. To estimate them in practice, typically we rely on some kind of assumptions. So researchers typically make two kinds of assumptions. The first one known as exogeneity, which basically says there is no confounder between x and y. The second kind of assumption researchers typically make are so-called monotonicity. So in this binary case in particular, essentially says if x is not true but y is true, then if x becomes true, then y becomes false. This probability would be 0. So it's kind of a monotonic, x monotonically influences y in some sense. So that's the kind of intuition. It has been shown that under these two assumptions, then this three probability of causation will become identifiable. So they can be expressed in terms of observed quantities, like those observed probabilities. So that's kind of the original theorem of POC. So they have been widely used in AI in different applications. Whenever you need to kind of provide a causal explanation or assign blames, assign responsibilities, and so on. So recently, this concept has been extended to discrete variables. So that's in a very recent paper by Li and Per. So here in this talk, I'm going to try to extend this concept to continuous variables. So now we assume that both treatment and outcome x, y are continuous variables with certain domains. So here is our proposed new definition for this 3 probability of causation for continuous variable y. So the intuition is basically we kind of introduce a threshold. So this lowercase y basically says now we consider the necessity and the sufficiency of a treatment x1 versus treatment x0 to produce this event that this y, outcome y would be larger than certain threshold y. So one way to think of this, you can consider binarize your treatment variable, the outcome variable y. So now we consider this event y is larger than y, given now we consider these 2 treatments. So this is our new definition. So essentially, it can be shown that under this interpretation, this new definition, it can be reduced to your initial definition for binary variable y. So this is very similar to this original definition, y equal to y1 or y equal to y0. Now we essentially replace them with this event of y larger than y or y is less than this threshold y. So in some sense, this is a kind of straightforward extension. They satisfy the properties of those original intuition for the probability of necessity and sufficiency. So here is an example to show the meaning of these quantities. So if you think about dose response relationship between the amount of insulin X and the blood sugar level Y. So we know that if the patient takes the insulin to reduce the blood sugar level Y. So you can imagine, let's say Y, little case Y is some kind of the threshold. We want to take the insulin to reduce the blood sugar level Y to below this threshold Y. And you consider 2 kind of insulin amount X0 and X1. Say X0 is a larger dose and the X1 is a lower dose. So if you think about this quantity of probability of necessity, so given that currently the patient took this small amount X1 and it has a blood sugar level greater than Y, we ask question, had the patient taking a larger amount X0, insulin amount X0, what's the probability that the blood sugar level would now be less than Y? So this intuitively quantifies the necessity of this taking a larger amount X0 versus a small amount of X1. Similarly, we can define the probability of sufficiency and the probability of necessary and the sufficiency of this taking the drug, taking the amount x1 versus taking amount x0 in causing the event that the blood sugar level will reduce to less than the threshold 1. So that's the definition of POC for continuous variables. So now, again, they are defined in terms of those counterfactual quantities that are typically not observable from data. So we make similar assumptions to identify them. So we have basically similar assumption. The first assumption is the exogeneity assumption. Now it's essentially extended to continuous variable. Again, intuitively, it's basically assumed that there's no confounder between x, y. And there's also a similar monotonity assumption. Now it's defined over this potential outcome variables. It's now a continuous variable. And I will not go to details, but intuitively we relax the original assumption a little bit, which can, by assuming either it can monotonically increase or you can monotonically decrease. So either one of them. Under these two assumptions, we can show that these quantities we defined are identified in terms of the observed quantities. So more specifically, they are identified in terms of conditional CDFs. So this is the definition of these rho functions. So this kind of extension to continuous variable is somewhat straightforward. But it turns out that, well, once we have continuous variables, now you can think more complex quantities. In practice, there are many other interesting causal questions researchers might be interested in. So with this continuous variable, then we could, in principle, define many other interesting causal quantities. For example, here we could define the PNS with evidence. So for this particular example, what kind of evidence? Here we can, for example, for the insulin example, we can consider the scenario that we can define the PNS for a particular kind of subpopulation for those patients who have taken the drug amount of X prime and currently had blood sugar level Y prime. We ask for this kind of patient. So we condition on this kind, we call it evidence. For this kind of a patient, what's the probability of, say, necessity and the sufficiency of, say, X0 versus X1 in causing the blood sugar level to be, say, lower than some threshold Y? So this is a new kind of quantity. We call it PNS with evidence. And we have shown that, well, with the same assumptions, this quantity is also identifiable. So here is the expression for this PNS with evidence. So as another example, now we can consider more complex counterfactual quantities. For example, for quantities like this one. So now we are talking about multiple counterfactual or potential outcomes. Again, for this, for example, for this insulin example, now you can imagine that in general, the overdose of insulin may cause too low, the blood pressure to be too low. That's also harmful to the patients. So we can consider scenario now we have two thresholds, like say a lower threshold Y1 and the upper threshold Y2. We have this two kind of threshold. What we want is we want the insulin level, for example, X1, such that your blood sugar level should be between Y1 and Y2. So you can consider, say, now 3 insulin amounts. Say X0 is the largest dose, and X1, X2, and so 3 different kind of dose. So as a doctor, you might be interested to say what kind of the dose X1 is, say, the best or better than X0, both X0 and X2. So now you can consider this kind of 3 counterfactual situations simultaneously. So we ask question like, we want the patient blood sugar level would be less than the lower bound Y1 had taken X0 amount of insulin. The blood sugar level would be greater than Y1 and less than Y2 had taken X1 amount. And the blood sugar level would be greater than upper bound Y2 had taken X2 amount. So this kind of 3 different counterfactual statements simultaneously. So we would be interested in asking what's the probability of this kind of counterfactual statement. So we call this the POC with multi-hypothetical terms. So in general, we might consider multiple those kind of counterfactual statements. So we may define this kind of POCs. With here, we assume there's a P different counterfactual statements. And again, we show that under the same assumptions, this PNS with multi-hypothetical terms is also identifiable. So it's estimable from the observed distributions. Okay, so that's basically our recent work to extend the standard definition of POC for binary variables to continuous variable. So the idea is now you might be able to define kind of very complex counterfactual statements and to try to capture some causal questions you might be interested in asking in your particular applications. So we show basically under similar assumptions, they might be identifiable and estimable from the observational data. So now in the second part, I briefly discuss causal mediation analysis for POC. So causal mediation analysis is about how the treatment influences the outcomes through different pathways. So we talk about the direct effects and the indirect effects. Here our goal is to extend this kind of analysis to the POC analysis. So now we are going to talk about the necessity and the sufficiency of a treatment in producing an outcome through different pathways. Here is the problem setting. So now we have X is the treatment, Y is the outcome. So we assume there is a mediator M, so that there's essentially say X can cause Y directly, or X can cause Y indirectly through this mediator M. And here we are also assume that there is observed confounder C between X and Y. So this is our problem setting. Now in the causal mediation analysis, people are interested in what's the effect of X, Y, say, directly through this path without going through the mediator M. Or in some scenarios, people ask what's the effect of X, Y that just goes through the mediator M without the direct path. So that's kind of the goal of mediation analysis. So if you assume the models are linear, so this kind of direct effects or indirect effects are kind of easy or straightforward to define. You just look at the path coefficient and you can define direct effects, indirect effects. It turns out for the nonlinear models, it's not that straightforward to define our intuitive concept of direct or indirect effects. Here I'm going to adopt the Peirce definition of direct and the indirect effects. So this particular definition have been very popular in the past like 20 years. So here is the Peirce definition of this direct effect and the indirect effects. Now first, normally people just compute this so-called average causal effect. So that's the potential outcome of y under intervention of x minus potential outcome of y under the intervention of x prime. You compute the difference, compute the expectation. So that's the typical so-called average causal effects. And here we'll call this the total effect, since it includes the effect both through this direct path and the indirect path. Now, in order to capture this our intuitive concept about direct effect, the first definition of this is known as controlled direct effect, in which we fix the mediate m to be a particular value of m, and then compute this effect. So this is known as controlled direct effect. So the effect of x on y when you fix the mediator to a particular value. So of course, this quantity depends on which value you fix. Now, another interesting quantity is called the natural direct effect. So this one is defined as, imagine you change x from x prime. You're setting x to x prime to x. But you keep the value of m, the mediator, to be their natural value when you set x to be x prime. So that's what this quantity about. So this particular quantity is known as nested counterfactuals. So if you can formally define them in terms of framework of structural causal models. But here I will not discuss the details. The intuition is essentially saying I switch x from x prime to x, but I keep the value of m to be the initial value when x had been set to x prime. And intuitively, this kind of measures this particular effect through direct paths, not through m. So this is called the natural direct effect. And then we have this definition of natural indirect effect. Intuition, I want to capture the effect that just goes through the mediate m, but not the direct one. So this one is defined as if you switch, say, x from x prime to x. But here you keep the value for x to be x prime. We just change the value of m from take the value when x is set to x. So versus this one is essentially saying m takes the value when your x is set to x prime. You compute this difference. And intuitively, this says essentially you keep the x, stay x prime for this path, but you just change the value of m here. And this captures so-called natural indirect effect. So those are the original definitions of direct and the indirect effects. So what we aim to do is kind of introduce this kind of concept to analyze the probability of causation. Oops. What's this? Okay. Whatever it is. And also, before doing that, since in these settings we consider there's a set of covariance C, observe the covariance C. So we can generalize our definition of POCs by conditioning on all those covariants. We call it conditional POC. Again, the intuition is you can compute more refined quantity that you can compute this POCs for those subpopulation in the particular subpopulation where all the subjects have this particular feature value C. So it's kind of more refined quantity. So to generalize the POS to the direct and the indirect effects, we'll focus on this PNS. In particular, this is the definition of the PNS, now conditioned on this covariance C. And now to distinguish direct and indirect effects, we'll call this the total PNC. So the total PNC essentially is saying if you change x prime to x, you want when x is prime, x equal to x prime, the potential outcome is less than y. When it's x, it will be larger than y. So this is the total PNS. So now we would like to introduce direct and indirect PNS. The intuition is we want to answer this kind of causal questions. So assume that you have established a treatment is necessarily sufficient to a particular event by PNS. You might ask questions like, would the treatment be still necessary and sufficient had the values of mediator being fixed to a certain value? Would the treatment still be necessary and sufficient had there been no influence by the mediator? Would the treatment still be necessary sufficient had the influence only existed by the mediator? So we want to answer this kind of causal questions. And here is our definition. So similar to Peirce's original definition, we now define controlled direct PNS and the natural direct PNS, natural indirect PNS. So intuitively, this basically, let's pick one particular example. Let's say controlled direct PNS. This one is a direct extension of the original PNS, where we simply set the mediate M to be a fixed value. So we fix the mediate value to be fixed. Now we ask the question, if you change x from x prime to x, what is the necessary and sufficiency of it causing y to be larger than y? So this one is a relatively straightforward extension. And then we have this so-called natural direct PNS. It basically consists of two counterfactual statements. We ask what's the probability of these two counterfactual statements being true. The first statement is essentially saying the original counterfactual requirement for PNS. So now we introduce another condition. So this one is essentially saying if you change for x from x to x prime, but you keep m with the same value of x when x is actually set to x prime. And you ask what's this, whether this will, so if you set x to be x, the outcome larger than the threshold, but you set x to be x prime, but m keep to the original natural value, the outcome would be less than y. So two kind of counterfactual statement. Similarly, for the natural indirect PNS, which try to capture the PNS through this path. So it's again defined in terms of two counterfactual statements. While we switch x from x prime to x, but keep m again stay with the same natural value when you set x to be x. So those are definition of direct PNS and the indirect PNS. And we can show that this new definition satisfies decomposition property. such that the total PNS is equal to the summation of the natural direct PNS and the natural indirect PNS. So it is a desired property. And finally, we could further extend these definitions to capture other complex scenarios. For example, we can define those quantities conditioned on certain evidence. So again, those are more refined quantity. You're saying you want to know this PNS for certain subpopulation, which characterized by some evidence. More specifically, we consider one kind of evidence would be for those kind of subjects which actually currently taken the treatment X star, and their current outcome is within this range. For this kind of subject, you may ask this the causal question of how X influence Y. So we call those the CDPNS, NDPNS, NIPNS with evidence. Also, you can show that so far I have focused on the PNS. There's all those similar concept of probability of necessity, probability of sufficiency. You can define all of them, define their corresponding version of direct effects and the indirect effects. It turns out all those can be naturally defined in the form of this PNS given certain evidence. So I will not go to the details. And finally, we showed that while we could provide identification conditions for these new quantities we have defined. So their assumption essentially follows the standard assumption in the literature. So in the literature for the causal mediation analysis, they typically assume so-called sequential ignorability assumption. It's two kind of conditional independent statement among counterfactuals. Intuitively, it's essentially saying there is no unobserved confounder, say between X and M, between X and Y. There's no unobserved confounder between M and Y. So those are the kind of the assumptions researchers have made for causal analysis, for causal mediation analysis. And we also make the standard assumption about the monotonicity assumption, which researchers make to identify those the probability of causations. So we show that under this kind of assumption, all these quantities we have defined, they are also identifiable in the form of some kind of conditional CDF. So you can use existing method for estimate this conditional CDF, and which in turn will be able to estimate those new quantities we have defined. Okay, finally, let's apply these quantities to a real-world data set. So we have considered this so-called jobs data set, which is randomized job training intervention data. So you perform job training intervention for unemployed subjects. The goal is to increase the prospect of reemployment and improve their mental health. Here we pick random variable X to be the job training assignment. So you randomly assign subject to control group and the treatment group. In the treatment group, I think subject go to the job training workshops. So they teach them how to find jobs. In the control group, they give subjects just the booklets of job searching tips. So that's the intervention. The outcome here, we consider a measure of depressive symptoms. With a certain threshold, then you consider depressive or not depressive. For the mediator, we use this quantity called job search self-efficacy. So that is a public dataset called jobs dataset. So the idea is we are going to apply those quantities to answer this kind of questions. Would the job intervention be necessary and sufficient to cure the depression had the job search self-efficacy being fixed to a certain value? Would the job intervention be necessary sufficient to cure the depression had there been no influence by this mediator job search self-efficacy? Would the intervention still be necessary sufficient to cure the depression had the influence only existed by the job search self-efficacy? So we basically compute those quantities like CDPNS, NDPNS, and NIPNS to answer those questions. So we use the standard basically CDF estimators. So here is our estimation result. First, we estimate the PNS is 23.8%. And now if we compute those control direct PNS, natural direct, natural indirect PNS, it turns out the natural direct PNS is basically close to 0. And all the PNS is actually equal to this natural indirect PNS. So essentially, for this particular data, based on those quantities, it seems that the necessary and the sufficiency of the treatment is entirely due to the indirect influence by the mediator. So we believe that these quantities will provide some kind of meaningful, more refined understanding to this kind of the data, to have a detailed understanding of how this job intervention influenced the outcome. Okay, in conclusion, we have provided a number of formal measures for several variants of probability of causation. The idea is to quantify the likelihood of one event being a necessary or sufficient cause of another, either directly or indirectly. So intuitively, those are the quantities we often ask in a number of AI applications for when you need to, say, make certain decisions, when you try to provide some causal explanations. In other situations, when you try to assign responsibility or blame, for example, someone, say, took a drug and died, you want to, how do you assign the blame to the, say, drug company and so on. So those are some of the causal questions we often need to ask in practice. So here we provide a formal mathematical definition in order to capture those kind of human concepts. And we also provide the estimation method and identification assumptions such that we may be able to estimate them from observational data. So we believe these results offer valuable tools for addressing complex causal queries in practice. Okay, 1 minute. Yes, I'm conclude. So for the potential future work, so one limitation of this work is the identification of these quantities relies on a number of assumptions like those exogeneity assumption, monotonicity assumption, and so on. So in many applications, you may not feel comfortable to make those assumptions. And one direction to address that limitation is, instead of trying to find a point identification, people try to use bounding technique. Say, can we find a range for those quantities instead of point identification? So that's a potential interesting future direction. So this kind of bounding have been applied for POS for discrete variables. But turns out for the continuous variables, how to bound them is basically unsolved open question. So another potential direction would be, here we talk about the direct effect, the indirect effects. And in general, people have studied like so-called path-specific effects. So we want to study the influence of treatment on outcome going through a particular path. You can think about very complex causal graph. You are only interested in a very specific path, causal path from X to Y. How do you generalize this concept to define this, say, POC for those kind of path-specific POC? That's also an interesting future research direction. Okay, this concludes my talk. Thank you.
So thanks for Professor Tian's talk. So do we have any questions here? We should have 1 or 2 questions from the audience. Yes, please.
Yes, thanks a lot for the excellent talk. So I'm just wondering whether you can talk more on the relationship between the use research, even the total causal this theory with the LLM, large number model. That means whether and how we can use the causal theory research to decrease the hallucination.
I don't know much about the LLMs, so I don't see how this theory can be applied to hallucination, those kind of questions. I guess I believe today we have a talk about that topic of causality and LLMs. That's LLMs beyond my expertise, so I don't know whether they are useful or not, whether this whole idea of whether causality, causal inference could be applied for solving those kind of LM problems or not. Maybe we will hear, in another talk, we'll hear all about it.
Thank you.
I wanted to ask you, so one of the confusing things about this whole research area is that you have these quantities where 2 counterfactuals appear that are directly contradictory to each other, right?
Right. That's why they are called counterfactuals.
Well, yeah, but it's a bit more extreme, right? Because you have
but that's kind of question people a lot of time when we ask for explanations. Like, for example, that particular someone took a drug and died. Like, how do you say, sue the drug company, say this drug is responsible for this person dying? In fact, in the court of law, people ask the but-for question. Had this person not taken drug, would the person have died? That's actually the real question in the court of law. That's how you establish it. This is a counterfactual question, right? So
that is all true, but it goes a little bit beyond, because you have a quantity where you're saying, what if that person took the drug and his cholesterol level depended on him not having taken it? It was as if he had not taken the drug, right? So
you have those conflicts saying, yes, had this person take this drug, would have had the person take the different drug, and you know the person cannot simultaneously take this, say, 3 different kind of quantities simultaneously.
It's called a cross-world assumption.
Yes, but I think with the natural effects, what I struggle with is you have these quantities where it says y, x, and then mx prime, right? So you're not just doing a cross-world thing, you literally
that's called nested counterfactual. Yeah. You are saying you keep m to the original value that with one x at a different value. But all these quantities, in principle, again, they are trying to capture our intuition, saying what we mean by this direct effect. If we're saying we only care about this path, now I want to keep the other quantities to some value. Instead of fixed value, we say their natural value they originally would take if you under a different setting. Right, that's the idea is this counterfactual trying to capture our intuition. Mathematically, if you accept, say, structural causal model, if that's our underlying mathematical model for governing the whole environment, then they are well defined in this model framework. So the definitions are well defined if you accept the SCM framework.
Yes. So in other words, okay, I get that logic. So if you have an SCM, you just plug one x in one. And
right. In principle, they are all well defined. So it's basically, it's like if we accept there's this underlying deterministic models there, you accept that as your model, then these quantities are well defined in that sense.
And what do you think about these discussions about separability to be able to talk about these quantities? Do you think they are necessary, or because you seem to have avoided them, right?
Right, because this whole framework, we use the SAM framework. Once you accept this, then this we assume this is the underlying model. Everything else defined on top of it. So I guess the debate is for us is, do you accept this model or not? If you are not willing to accept this model, then perhaps you need to build a different framework you are happy with. I guess for us, the whole mathematics theory are built over this model. So we assume this is our underlying causal model. At least that's self-consistent to me. So all those quantities, they are well defined. And the main issue is we believe those are the quantities we human beings think about. Like whenever we talk about the explanations, we ask all these kind of counterfactual questions. So here we have a framework trying to basically provide the mathematical framework to answer them, I guess. That's my understanding.